Hello, welcome to Chingster's video on conditional probability. You might not have heard of conditional probability, but you would have applied that in solving some probability problems in your earlier years. So let's look at some examples and derive the formula. We're going to look at two different situations. First, I'm going to look at, say, a situation where you have 10 discs and you want and out of the 10 discs you have 3 red ones and 7 blue discs. So we're going to have two different situations. So situation 1, we're going to have, you're going to pick 2 discs and you will do it with replacement. So that means after you pick one disc, you will put it back into the pile. So now if I look at it using a tree diagram, we're going to have the first pick, second pick. So we're going to have, say, the red first, and then the blue. So the red, the probability of getting a red in the first pick would be 3 out of 10. The blue will be 7 out of 10. And for the second pick, because we are replacing the red after we pick it, so the second time you get a red is still 3 out of 10, and for the blue is still 7 out of 10. And for the second pick, when you first pick a blue, what is the probability when you get a red? Again, it's still 3 out of 10. And for the second pick for blue is 7 out of 10. As you can see the outcome here, we have red, 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 blue, blue, red, and blue, blue. And for the probability of each case, this will be 3 10 times 3 tenths. You get 9 out of 10. You get, second will be 3 tenths times 7 over 10, 20. Sorry, it's 9 out of 100, and then you get 21 out of 100. And the third one will be 7 tenths times 3 tenths. You get 21 out of 100. And then for blue, blue will be 7 tenths times 7 tenths. You get 49 out of 100. As you can see, the events are independent events. You can actually just multiply the probability to get the total probability. Now we're going to look at a second situation for repeated events without replacement. So you're going to pick 2 discs without replacement. So I will draw this again. So we have the first pick. We have the second pick. So the first pick we have red and blue here. So the probability of picking a red for the first pick is 3 out of 10. The blue will be 7 out of 10. Now for the second pick, we have the red and the blue. Now we're going to be careful here. So after you pick up one red, the total number of discs will be 9. And how many remaining red will be? 2 out of 9, right? And for the blue will be still 7, but the total is now out of 9. And for when you pick a blue one, for the second pick for red, you still have 3 red, so 3 out of 9. And the blue will be 6 out of 9. So if we look at the outcomes, we have still the red, red, the red, blue, the blue, red, and blue, blue. And the probability will be 3 10 times 2 9s, and you get 6 out of 90. The second case where you have a red and the blue will be 3 10s times 7 over 9, you get 21 out of 90. And third one, the blue red, will be 7 out of 10 times 3 out of 9, you get 21 out of 90. And for blue will be 7 out of 10 times 6 out of 9, you get 42 out of 90. And you can see for the four situations, when you add them up, you should equal 1, just like for the first case. They should equal to 1. Now if we extend the situation to a more theoretical situation. So now we're going to look at the two events of A and B. So if we have A happening and the complement of A when it's not A happening, and we have B happening and the complement of B, and we have the second situation of B and the complement of B happening. So in this case, when you have probability of A happening is just PA, and the probability of A complement is PA complement. Now, in your second choice or second pick, the probability of your B happening will be your probability of your B given your A has happened. In this case, this is the first branch is A. And so the second will be probability of B complement given that A has happened. Okay, and the second situation, once you pick A complement, you will have probability of B happening given that A complement has happened, and then probability of B complement happening given that A complement has happened. The mathematical notation PA bar B is read as the probability of event B occurring given that A has occurred. So given that A has occurred. So if we look at the situation on the right hand side, so this will be, just like we multiply the probability here, it will be PA intersects with B. This is PA intersects with B complement, PA complement intersects with B, and this is PA complement intersecting with B complement. So this brings us to axiom 4. P of A intersect B is equals to probability of A multiplied by probability of, if we look at this branch here, right? So would be probability of A multiplying by probability of B given A. If A and B are independent, then I can say that probability of B given A is equals to probability of B. Just like the example in our first case. In this example here, we just multiply the probability here. So in this case, therefore, probability of A intersects with B is equals to probability of A times probability of B. For theorem 3, we have probability of B given A plus probability of B given A complement is equals to probability of B. As you can see here, for each branch here, for example, here, these two add up to give you the probability of B, and for the second branch, these two add up to give you the probability of B. So now you can fill in your notes if you haven't done this. So probability of A intersecting with B is equals to probability of A times probability of B given A. If A and B are independent, then probability of B given A is equals to probability of B. Therefore, probability of A intersecting with B would be probability of A times probability of B. Now, for theorem 3, probability of B given A plus probability of B given A complement is equal to probability of B. Now let's do some example for practice. There are 52 cards in the regular pack of playing cards. Marie draws one card. Find the probability that Marie has drawn a black ace. So we can represent this in the Venn diagram. So we have ace, and then we have black. So we know that there are four aces, and two of them are red, two of them are black, so it's 2-2. And and there are 26 black cards, so this will be 24 here, and the rest of the cards will be 24. This is a universal set. I'm gonna get A be the event that you get an ace, B be the event that you get a black card. So the probability that, so PA in this case will be 4 out of 52. Probability of B will be equal to 26 out of 52. Probability of A intersecting with B will be equals to 2 out of 52. And probability of A given B, if we use the formula, let's first look at this probability of A given B. If I use the formula, it's actually PA intersecting with B. Let's look at how we play around with this first. So this formula, if we have PB given A will be equals to probability of A intersecting with B over probability of A. So I'm going to apply this here. So P of A intersecting with B will be P of B multiplying by P of A given B. So in this case will be, therefore I can say that probability of A given B is equals to probability of A intersecting with B divided by probability of B. In this case will be 2 out of 52 divided by 26 out of 52. And if we simplify that, you get 2 out of 26 as the answer. What does this mean when we go back to the Venn diagram? So the probability that is drawn a black card, you can see the total is out of 26, right? And then the probability of getting a black is actually 2 here. So it's 2 out of 26. Now let's look at example 4. The probability that a train is late is 0.3. If the train is late, the probability that Florian will make it to work on time is 0.6. If the train is not late, the probability that Florian will be on time for work is 0.9. Let A be the event that the train is late and B be the event that arrives at work on time. So part A, draw a tree diagram to represent this event. So we're gonna do part A. So you know that we have probability of A, which is the train is late, and probability of A train is not late, which is A complement. And then we have the probability of Florian arriving on time and probability of Florian being late. We continue when the train is on time and B complement. So probability of A train being late we know is 0.3, and this is 0.7. And if the train is late, the probability that Florian will make it on time is 0.6. And so we know that B complement has to be 0.4 because they have to add up to 1. And probability of if the train is not late, Florian will be on time 0.9, and this will have to be 0.1. So now part B, find the probability that train is late and Florian is on time. So it's PA intersecting with B. In this case, we can just, so it will be probability of A multiplied by probability of B given A. So it will be along this branch, you will be 0.3 times 0.6, and the answer will be 0.18. Part C will be the probability that Florian will make it on time. So it would have to be we look at the on time will be this part here plus this part here. So if we want to write it out in terms of formula, we get PB is equals to probability of A intersecting B plus probability of A complement intersecting with B. So you end up with 0.18 that we found earlier plus 0.7 times 0.1. So 0.18 plus 0.07 will be 0.25. With regards to using the notation, this is actually PB given A, this is PB complement given A, 0.9 is PB given A complement, and this is probability of B complement given A complement. For part C, show that the train being late and Florian being on time for work are not independent events. So we want to show that if they are independent events, if A and B are independent, we know that probability of B given A is equal to probability of B. That is, probability of A intersecting with B is equals to PA times PB. In this case, P of B given A is not equals to probability of B, as we can see. Probability of B is 0.25 and probability of B given A is given by 0.3 times 0.6 is 0.18. Yeah, they are not equal. It's not equal to 0.25. Another way we can consider the situation is to find out whether probability of B given A plus probability of B given A complement is equal to probability of B. So probability of B given A is 0.18 and probability of B given A complement will be 0.63, and that's not equal to 0.25. So therefore they're not independent. Next, please try the investigation 3. We're going to learn more about Bayes' theorem, and give yourself to complete this investigation and check your answers with the solution available on Teams. So the key ideas is if B sub 1, B sub 2, B sub 3, all the way to B sub n is a finite set of mutually exclusive events, then the probability of B sub 1 union B sub 2, union B sub 3, and so on, and union B sub n will be equal to probability of B sub 1 plus probability of B sub 2 plus probability of B sub 3 plus plus probability of B sub n. And B sub 1 union B sub 2 union B sub 3 union and so on B sub n, they are equals to the union set and they are exhaustive events. And the word exhaustive in probability means that at least one of them will occur. For axiom 1, probability of the universal set will be equal to 1. And A is an arbitrary event of the sample space for I equals to 1, 2, 3, so on up to n. It follows that for Bi given A, it will be probability of Bi, B sub I, given times probability of A given B sub I, and the denominator will be probability of A given B sub 1 multiplied by probability of B sub 1 plus probability of A given B sub 2 multiplied by probability of B sub 2, and so on, plus dot dot dot, plus probability of A given B sub n multiplied probability of B sub n. If two events A and B are such that A union B equals to U, where U is the total probability space, then probability of A union B will be equals to 1. And the sets A and B are said to be exhaustive. If you have your formula booklet, I would like you to look at the formula booklet to locate where the Bayes theorem is located. It should be in topic 4, 4.13, page 7. So, and from the formula booklet, you are given PB given A is equals to PB times PA given B over probability of B times probability of A given B plus probability of B complement times probability of A given B complement. And for extension, when you have more than two cases, so you two events, so you have PBI given A is equals to P of BI multiplied by P of A given BI over, it should be I, and then will be P probability of B sub 1 times probability of A given B sub 1 plus probability of B sub 2 times A given B sub 2 plus dot 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 plus probability of A given B sub n. So let's look at example 1. In a school, there are 60% male teachers. Of the male teachers, 30% teach DP Maths, while 80% of the female teachers teach DP Maths. Given a randomly selected student is studying DP Maths, find the probability that the teacher is female. So we have the situation here. Probability of male is equal to 0.6, and the probability of not male would be 0.4. Probability of DP given male is 0.3. So the probability of DP given or not DP given male would be 0.7. And probability of DP given not male is 0.8. And probability of DP complement given a female teacher is 0.2. So if we look at this in the diagram, is we have M and then M complement DP, DP complement, and then DP, and then DP complement. So we know this is 0.6, this is 0.4, this is 0.3, this would be 0.7, and this is 0.8, this would be 0.2. So in this case, we want to find the probability of male, not male, given that it is DP. The formula will be probability of not male times probability of DP given not male over probability of DP. So in this case will be, and we know that for probability of DP is equal to probability of DP given male times probability of male. So we know that is this branch, and we know the other branch will be here, plus probability of DP given not male times probability of not male. So this will be 0.3 times 0.6 plus 0.8 times 0.4, and the answer will be 0.5. And so the final answer for this will be, so for probability of female given the DP student will be 0. So probability of male multiplied by, so this branch will be here, so 0.3 0.32 divided by 0.5, 0.64. In our next example, 3 students, Lauren, Maddie, and Georgie, work in a coffee shop. In any given hour, Lauren will make 55% of the coffees, Maddie will make 35%, and Georgie will make 10%. The probability that Lauren, Maddie, and Georgie spill some coffee is 0.6, 0.2, and 0.1 respectively. Given the coffee is spilled, find the probability that it was served by Maddie. So now I'm going to let A1 be the event that Lauren serves the coffee. My Apple Pencil has run out of battery, so A2 will be the event that Maddie, and A3 will event that Georgie is serving the coffee. And if you represent this on a tree diagram, you got A sub 1, A sub 2, and then you have A sub 3. And the probability for each case will be, this will be, I think, 0.55, and we have 0.35 and 0.1. And when you extend it to the next situation, which is spill and not spill, will be S and S prime, S complement, S and S complement, S and S complement. So you're gonna end up with, so this is 0.6 and S complement will be 0.4. And for the second case, 0.2, and you get 0.8 here. And for event or for Georgie will be 0.1 and 0.9. So you require probability of A sub 2 given S. So will be, and that is given by probability of A sub 2 times probability of S given A sub 2, and the denominator will be probability of S given A sub 1 times probability of A sub 1 plus probability of S given A sub 2 times probability of A sub 2 plus probability of S given A sub 3 times probability of A sub 3. All you have to do is to follow the formula and substitute in the value. So we're looking at which branch here? We're looking at all the situation when it is spilled. So this is all the possible sample space. And from there, when we work it out, we will get 0.45 times 0.2 over 0.6 times 0.55 plus 0.2 times 0.45 plus 0.1 times 0.1, and your answer will be 0.209 given to 3 significant figures. We reached the end of the video. I hope that you can follow and understand. Thank you for your time. Don't forget to do the practice questions available in the booklet. Bye.